Welcome back to the Pre-Vetted podcast, where we spotlight extraordinary people and remarkable talent reshaping our world. Today, we're joined by Dominique Roddier. I pronounce it correctly?
Good enough.
Great. He's a naval architect and CEO of Ossurgy, a company building sustainable offshore solutions for clean energy. Before founding Ossurgy, Dominique spent decades designing complex ocean systems for offshore wind and other renewables, becoming a lead voice in floating wind technology and ocean engineering. With climate impacts already visible across our oceans, we're going to talk about global warming, what is happening on our planet right now, and how offshore innovation can help us change course. Dominique, welcome to the show.
Thank you, Federico.
This is a beautiful view, by the way. We are in the marina, right?
Yes.
It's a lovely day, so it's an amazing venue to have a great conversation.
Yes.
Yeah.
And it was late November, and we're wearing a shirt in Northern California. So talking about climate change, there is some benefits.
Right.
Even though we'll talk more about the negatives than the positives.
We should be, having a jacket, and we don't have to. Yeah. So tell us, how did you fall in love of the ocean?
So I was born in the south of France, close to the ocean. Some people in my family were very much involved in the shipping industry and sailing. And when I was a kid, I just wanted to be the captain of a tanker. And you asked a 7-year-old, why a tanker? And I would say it's the biggest ship out there. How did I know that? I don't know. But I've spent my summers sailing and became a sailing instructor and wanted to study naval architecture. And I am one of those few people that studies what they love and are working in what they studied. So I don't take it for granted. I'm extremely lucky.
Right. I think that there is I'm a romantic, right? So I feel there is a romantic concept of the ocean, right? Because it's both, the adventures, what the unknown, right? The danger, right? It's unforgiving, right? Which also help us build this discipline, right? And then I've seen it as an outsider, right? But I see the camaraderie, right? That is around, every sailor to be that, it brings them together, right?
Yeah. You also find this in the mountains, in the mountaineers, this camaraderie. And that's why usually they get along really well. But it's true. I mean, we're very close to the environment. It's a very dangerous environment. So there has to be a respect of the forces. And so people are usually humble. If you find yourself in a storm in 3-4 meter seas, you're small. And knowing that the biggest storms are 20 meter seas, you can only imagine that how tiny human beings are. What's also interesting with the ocean, Sylvia Earle is one of the famous American oceanographer, has a few books, and one of them she talks about space and ocean and how everyone is attracted to space. We've been to the moon, we've sending probes, but we've never been all the way to the bottom of the ocean, our own ocean. We haven't mapped it out totally. And there's this thing about, we want to do it. But some people, I've flown a lot, but I have no desire to learn how to fly. But I love to dive. I love to swim. I love to sail. So, it's
that's what I was using the word unknown, right? Because we can, there's so much to explore, right? Yeah. Actually, next time you come to Guadalajara, Mexico, we can go to, there is a lake that people say that it's bottomless.
Yes.
Very distant, but
yes.
It's good to have that myth of, because it was created by the volcano.
Mm-hmm.
So and then the mountains around it. So then they haven't been able to go to the bottom, right?
That's
Which is, what you're talking about.
It's deep.
It's deep. Yeah. And that
is deep and scary, and some people are attracted to it. We have the same in a lot of places in Europe, in France as well. But there's not that many people that want to go there.
Right. Right. It's a
special breed of people.
Yes. That's why I call it adventures, right? It's you have to have a je ne sais quoi, to call you to go and explore, and push the limits of what we can actually do, right, as humans, right?
That's right.
Yeah. And I like the concept of how bring us to humility, right? Show us how small we are compared to the world, right?
I think that's a very key point of everyone that goes out. People that are not humble find themselves in trouble very, very quickly. So,
right. So for people that don't know, what does a naval architect actually do?
Yes. So we design things that go in the ocean, floating or fixed. There are two parts to naval architecture. One is understanding how the ocean affects the structure that you're designing. How does the structure move due to the waves? What are the forces that the wave put on that structure? It doesn't matter whether it's a small wave energy buoy or a huge oil and gas platform or a ship or wind turbines. We'll talk about those. It's the same concept. It's just something that is in the water. So the first part is understanding how that moves. That's called hydrodynamics. Hydro from water and dynamics from moving. And then the second part is, given those forces, how do you design a structure that sustain those structures, that doesn't collapse, that doesn't sink, that doesn't break down? And so that's really structural engineering. So in a sense, naval architecture is not an architecture. My wife is an architect. She designs beautiful things. We don't really we design what I think of is beautiful, but it's not to be attractive to the eye. We design efficient structures to go in the ocean. So first, the hydro, and second is the structure. Talking about architecture, I was 5 or 10 years ago, I was giving a talk at the AIA, which is the Architecture Association from her. And I took, so we don't see it, but some Francisco stories on the background over there. And we have one landmark building, which is the Transamerica Tower. You've probably seen it. I had taken a picture of the Transamerica Tower. I have put it sideways in the bay under the Golden Gate. So Photoshop with the other building. And I was telling the architect that everything that's on their structure, we have mechanical, plumbing, electrical things, but we're not connected to the earth. So we're self-sufficient out there.
Right.
But that's really kind of the same thing. It's when we design things at sea, we have to be self-sufficient in terms of power, in terms of communication and survival.
Yes, self-sufficient, reliable, and everything has to be designed so it can sustain the worst weather. Yeah.
And we can't sink unless we're submarine, but then we have to go back up.
I mean, similar to the airplanes, that the airplanes cannot stop, in the middle to fix something. You can stop, but you cannot sink. Yes. Yeah. And I find that fascinating, that concept, because when you're getting into those type of trips, you're getting, you're putting your life on the captain's hand, right?
Yes.
And everybody's on the same boat, right? Quite literally. Right?
It's funny. It's the same, the captain of an airplane and the captain of a ship.
Yes.
Same word.
Yes.
The same thing. He's in charge.
He's in charge.
Or she's in charge.
Yeah. And the coordination of the whole team that makes everything happen, right? Because, single mistakes can make, Yeah. I was reading recently there was a boat, a Mexican boat that
yes, I heard that where the people fell down and died, and so it was tornadoed, and then it was on a current in the river, and the boat lost power and started going backward, and the people that were up in the mast were on the bridge. They cut the mast and 20 people died, I think.
Yeah.
20 of the mast. Yeah, it's a very, very sad story.
And that's, and it was supposed to be a routine procedure, right?
Yeah.
So everything they do when they're on the boat can become mission critical, right?
Yeah, I don't know a lot about what happened. I just saw the videos and I was heartbroken, but clearly there was multiple steps that did not happen. And why did those steps not happen? That I don't know. But first, there was a lot of boats and tugs next to it that we saw. Why didn't they come in? And those boats have anchors. Why didn't they drop the anchors? That was my first reaction. As the captain sees that he's drifting towards the back, you try to stop the boat. And I think that the other thing that happens is people freak out in those types of things. So I think there was definitely an element of, okay, this doesn't work. And eventually you run out of time. So preparation and practice and making sure that all your safety. So in offshore work, we spend a huge amount of time worrying about safety. Right. And that's very important. When I started my career working for Exxon, and it was, everybody comes home, no casualties, no, taking care of the people. And you repeat it over and over and over again so that it becomes embedded in people's mind. And that's very important. People have safety minutes and you're like, okay, but why another safety minute? But it's this constant repetition that you have to think about safety. That's very, very important. But even though you do that, you still sometimes have tragedies.
Yeah, I think that what I've seen people react to these routine safety checks is that they lower the guard because nothing happened until something happens, right? Yeah. I told you before we started recording the episode that my godfather used to have a boat, and it was so much fun, when we were riding on the boat. But also, we were able to just. He had the emergency flares. They had to renew them every once in a while. So every time he had to renew them, he would bring the old ones, and then we would, just turn it on. Just for the fun of it.
In France, we do this only one day on the 14th of July.
Oh, really?
Then we are allowed to use the old flares and put them out. Yeah, but that's the only day, and people know.
yeah, because it's I like to play with those things, but also I respect the use of security, right? So it's yeah, and I think I also told you about this that. I had a situation where I had to use the emergency button on the satellite messenger, right? Yeah. You have the red button. You want to press it to see what happens, but it's not an emergency, so you cannot. Yeah. So when it is an emergency, you have this feeling. Well, I had this feeling of so bad. It's bad we're in this emergency, but it's great that I can press the button, and see what happens, right? Yeah. And see how all the emergency procedures developed. Yeah.
And running out of alcohol is not a reason to press the button.
Sorry?
Running out of alcohol on the sailboat is not a reason to press that button.
I was wrong, so I pressed the button. Yeah. That doesn't fly. Yeah. Actually, because of that, we got a helicopter from the National Guard.
Oh, you did press?
Yeah. Okay. Because we got stuck on, so we were off-roading, and then we got stuck in the middle of the mountain, and we had winds of 150 miles going over us, trees falling over us, and then we got stuck for 5 days on the middle of nowhere. But the whole area was affected. So, they got our message and they sent a chopper to see how we were. But we had water. Because again, we prepare for a worst case scenario, right? So we had plenty of water. We have fridge. We have cold and hot meals. So we had more than enough, but it was just a matter of, we had a big boulder that blocked the way. So we had to build a bridge to drive the trucks over the boulder, right? And then we cut around 100 trees, so it was interesting. We had a first aid kit and everything, because again, it's the same mindset of, we're going into the adventure, but we want to also manage the risks, right? And we prepare for the worst case scenario, right?
So I know we'll talk about offshoring, but a friend of mine actually lives in the Bay Area, and he sailed across 2 oceans on a kayak, solo. And so it was very interesting because the first time he tried to do it, so he left San Francisco to go to Hawaii. That was his Pacific, and he just did the Atlantic last year. But the first time, so he was all ready and got into storms, and it was pretty big, and he was inside his cabin. And he had like a mental coach and very good preparation. And after 4 days, it was too much. And he pressed the button, and the coast guard came up and picked him up and brought him back. He left his kayak. And a few days later, he went to get his kayak back and brought it back. And then, so when he tells the story, so his name is Cyril Dereme. When he tells the story, it's much better. But then he tells the story about talking to his coach. And the coach says, well, you know what happened? And Cyril goes, and the coach goes, well, were you ready? And Cyril goes, no. Well, yeah, I was ready. Because I had done all of this. It's just, and then the coach goes, well, are you sure you were ready? And the term, then he starts changing, saying, eventually it's like, you got your boat back and your boat were fine. So were you ready? And I said, no, I was not ready mentally to prepare myself for that storm.
Right.
My boat was ready, but I was not. So the good part about the story is 2 years later, he went out and did it and kayaked single-handed. He's in the Guinness Book of Records, but he kayaked to Hawaii. And then this year he kayaked from Spain all the way to the islands, all the way to the Martinique. So
Wow,
he's twice in the Guinness Book of Records, and now he's ready to. And he gives seminars. I should put you in touch with him. Because he's very, very good person to talk to. Very enlightening.
That's amazing.
Yeah, I'll put you in touch with him.
Yeah, I would appreciate it. Yeah, it would be great. I think that for me, the appeal of these adventures is we learn from the failure, we learn from the success, right? I mean, the success happens after we failures, many times until eventually
we learn more from the failures than the success. Yes. The success is when we've learned everything we have to do.
Right. Exactly. Right. And having the courage to try to attempt it, right? Even though it could be, difficult, it could be challenging, and having the courage to then do it again, after you fail, that's
when you grow.
Yes. So I find those stories fascinating because I think that there is a lot of connection with, those type of adventures and running companies, because we also face on companies, we also face uncertainty, we face the fear to fail. There's so many, things that accompany us, right? So, yeah.
That's right.
So, when you look at the oceans today, what signs of global warming do you see most clearly?
There's a few. I mean, there's quite a few. Obviously, the temperature. The temperature has an implication when on the population, on the fish and everything that lives in it, has an implication on climate outside. The ocean is really what keeps the earth cool and warm. If we don't have the Gulf Stream, Norway will be under snow, so it keeps it warm. San Francisco here, the ocean keeps us cool. So it really regulates us. And when you start playing with your thermometer, then bad things happen. And the other thing that people don't really realize too much, but the global rise of the ocean, you can think what happens if we lose a meter here and those houses will float up? Not so much, but in the South Pacific, and people don't really think too much about that, but we've displaced entire populations from atolls to other atolls when we're doing nuclear testing. And those atolls are very, very low, 2-3 meters. This is also, very calm waters. But you take off a meter and then you're displacing those populations. The problem is they can't go back to where they came from because it's radioactive. So what are we going to do with those populations? As for me, that's I spent some time in Hawaii and I was very close to people from there. That's a big issue. Right, as well. So, where's our food source coming in? The fish, the type of everything. How do we deregulate the land temperature because of the water is down and global, level of rise of the ocean? Those are the big issues.
Oh, I see. So this is going to affect a lot of areas that are very close to the ocean.
Yes,
and also people that have low resources.
Yeah.
Right. And how How much does the temperature is going to affect the race of the water?
So it's the melting of the ice cap that really deregulates everything. And so this global rise is due on that. Everything is related. We can't just, one thing happens with the other, and then we can talk about, social impact on populations and things like that as well. But just going back to your question about the change in temperature, that has very, very big impact. The warmer the ocean gets, the more energy gets put into weather systems. So you start seeing major tornadoes, hurricanes. We saw the biggest hurricane ever that blew over the Caribbean a few months ago, killing, I don't know, hundreds of people. But you can't design buildings for 200 miles per hour wind. When this is your 100 case or your 500-year return period. So big. And I know I don't want to talk about the Paris Accord under COP and things like that, but I just have to say, we cannot 10 years ago or 15 years ago say, okay, we're very happy. We're only going to limit the temperature to 1.2, 1.5 degrees or whatever it is. That number should be negative, not positive. We're too hot already. We need to reduce. And people are just happy to set something and then exceed it. And it's not, the planet is not going to like it, and it's going to take us out.
Right. And the effects are, for our next generations.
Exactly.
Yeah, we were talking before about the how, that I have hopes, because I've seen how in the 90s, all the countries agreed to reduce the ozone layer. The ozone layer, yeah. And I believe that now it's almost 70 or 80% already, fixed, and it's going to be fixed in, I don't know, 5 years, 10 years, it's going to be completely fixed, right? So I have hopes that something like that will happen with climate change, right?
And now we start talking about renewable energy.
We haven't
Thanks for the lead.
Right, we haven't even talked about renewable energy.
But this is exactly right. I mean, burning oil and gas or coal heats up the planet. So decarbonization is a path to take us back down, removing the carbon from the oxygen. And I was at an plug and play investor event last week. There's many companies, one that I called Charm. So look it up, CHAR. And this is about removing carbon from and separating the carbon into a liquid and a gas and fertilizing. So there are technologies there. So right. we need to make sure that those technologies can be economical in some fashion. And then there's just not producing more for our electricity need. No one is saying let's go back to candles. Well, some people are, but we're not going back to candles, but we're going to efficiency and clean generation. That clean generation is what we need. And what I work on, floating offshore wind, but offshore wind in general, is a path towards that.
Yeah, I think this is a good moment to talk about, Ossurgy and what you're doing at Ossurgy, right?
Yeah. So Ossurgy, we're a technology company.
Right.
We're naval architects, so we develop platforms, solutions that go in the ocean. We have two. One is a data platform, and this is really to enable the bigger projects by having better data. And data is cheap compared to everything that for engineering is cheap, and data is necessary to be able to do very, very big project. So that platform measures everything that you need to do a floating wind project. There's a LiDAR that measures the wind up to 300 meters, measures so you can bank the projects that you're on. It's very stable, so you have very good quality, so we can measure the turbulence and so on. But then, so you take away, and then, wind, wave, current, and all that. And then you take away that part, it's very efficient because we also measure everything that has to do with biodiversity. So anything related to birds and bats, we see them fly in the background, making sure that our wind projects don't kill birds or know what's happening in terms of those. So know when the migrations are coming and the type of birds and so on. So we can live with them kind of the same way we have to live with, the navies and the fishermen and the NGOs and the shipping. We have to live with our environment as well, and we have to preserve it. And then everything that happens under the seabed. So under the water. So whales, dolphins, marine mammals, fish, larvas, type of things. So that's the first product. The second product is an offshore wind floater. So it's a floater that holds a turbine, and that turbine is connected to a cable that goes back to shore. So you have, you see onshore and offshore those big projects. The next frontier is to do it in deeper water. Why? Because 80% of our oceans and our sites are in more than 60 meters of water depth. So bottom fixed project where the turbine goes into the seabed. That's great for the North Sea and a couple of coastal places, but it's not good for a lot of the other areas where we need offshore wind. For example, in California, you go 2 kilometers off and you have 700 meters of water depth.
Right.
So
you cannot build a structure 700 meters.
That's right. Well, not very cost effectively.
Right.
So that's what Ossurgy is. But maybe a little bit more is, as an engineer, if you want to put things in the water, you have to do 3 things. One, you have to have something that works. So that's the thing that everybody cares about. But it's supposed to help your clients. So you have to address your client pain points. Otherwise, you're not going to have a client. And then you have to do it at cost, economically, so people can make money. Otherwise, they're not going to do it. And the older you get, the more reports you have in your shelf by your office of all the great projects you worked on. And the end deliverable is that very nice bond report that you once in a while look and say, oh, those were the good times when I worked on that. Very few people have actually worked on, a lot of people, but in engineering, it's nice when you get to the next phase, which is you get things in the water. And for that, you have to solve those 3 things.
Right. Otherwise, they are dreams, right?
Otherwise, they're dreams. And so in floating offshore wind, the first pilot was done in 2009 in Norway. The second was done in Portugal. And that was us, the first company that we did, called Principal Power. But what we've done with all those projects, those pilots, if we saw the first part, the engineering problem. We've shown that we can make a turbine spin on a floater. And there's 9 projects, 9 pilots in Europe and 6 in China showing that. And we have one right now that's being built or assembled for Ossurgy, for the new company. Then what we did for the second phase is we tried to reduce the risk. And we reduced the risk, how? By financing projects, but by having government subsidies that helped us. So every project that has been installed in Europe and worldwide by now in floating wind have had, it's not level the playing field, but they've had some type of government support coming from their countries or Europe or so on. Whether it was NER 300 for Portugal, it was the ROC coming from the UK, and so on. So now we know that we can reduce the risk so we can bank finance those projects. The next point is the hardest. How do we remove those subsidies and make the project work financially? And for that, we have to reduce the cost. That's very important because you cannot reduce the cost of something by saying, okay, I'm going to remove that part and that's going to be cheaper, because you're going to, there's so many parts in the cycle, in the life cycle of a project, that to reduce by 20%, you can't reduce by 50% or 100%. You can't take offshore wind and say, okay, I'm not going to use a turbine. Your cost is good, but you don't have a turbine. So what you have to do is you have to reduce the cost across the board by a little bit, 10, 15%. And it's only when you do that you have to look at your total outcome. And the best way to do this is industrialization. And this is really working with your supply chain, being very conscious of all your costs, understanding what it is, and making it work. So the best example that we always go back to for us is not in the aerospace or water industry. It's in the car industry. And it's the Toyota production system. It's how did Toyota become the first car leader in the US? over all the US companies
Right.
back in the 80s, 90s.
They implement just in time.
Exactly. And you look at, those two things. And that's exactly what we do. So we spend a lot of time looking at our supply chain, telling our supply chain, do not spend 300 million on investing to do floating wind. Let floating wind meet your requirements. Because if you want to invest 300 million, the first two projects will have to pay back that investment. And we will never be able to work with your facility. So you've kind of shut yourself out of that market. So it's understanding this, understanding your supply chain, understanding your contracts, and reducing the risk so you have better financial rates. Obviously, you need to start with a very, very efficient structure. So that's the engineering part at Ossurgy. I mean, we have the lightest structure. We're the first ones to actually bolt it together so it's connected with flanges. But exactly like the wind industry, I mean, the towers are bolted, so our structure is bolted. It's the same people. So we go fast.
Right.
If you spend 3 years doing a gigawatt scale project and you start your financing 3 years before you're producing electricity, that's very, very expensive money. So by the time you say, okay, my project is sanctioned, let's go, you gotta go as fast as possible. So a turbine, and we'll talk about the size of the turbine, but say a turbine is 20 megawatts, it's the biggest turbines out there. And you have a gigawatt scale project, around the same as a nuclear power plant. That means you've got 50 units. They're big units, but it's 50 of them. In 1 year, that's 1 unit per week. How do you put a structure that's, in our case, 4,000 tons, plus a turbine that's another 2,000 tons? How do you move them every week in and out with the turbine go out, turbine go out? That's industrialization. And that's what we work on.
Right. Because with that, you can reduce the costs.
That's right.
Right. Because if you have to do one-off for every single project, it's going to be much more expensive. So,
and this is kind of the first thing that this is done in the offshore industry, except during the World War II, actually here in the Bay Area, we used to send a ship every 2 or 3 days. And what happens is for all of the shipyards were building ships, but it's not like if shipyard was building one ship. It was like all the components were being built in different places, and some were building, some were assembling, things were moving, and the ships were going out.
Right.
It's the only time that I know, except maybe for small series of commercial sailing boats, where they're kind of identical, where you pick your options. Except for that, that's kind of put apart. It's more pleasure craft, and they're small. Everything else is always a one-off, and so we're trying to not do a one-off. We're trying to make similar units and reduce the cost and reduce the risk by keeping to those units.
Right, because if you can reduce the cost, it is more feasible to do. And then you're also reducing risks just by normalization,
That's
right?
Yeah.
And then it becomes, and I'm oversimplifying this, but when you go to a burger joint, you say combo 1, combo 2, combo 3, right? So, what do you need, client?
That's right.
Choose from this menu, right? So getting towards that simplification, right? And again, this is probably an oversimplification, right? But is this idea of modularization and being able to reuse the same design, so you don't have to rethink everything.
That's right.
Every time.
So that's what really we're trying to go to is one hole per turbine. So you change your turbine, we have a hole that works with you, and we try to really keep it the same, even though we might be in different areas with different sea states or minimum changes.
Right. So, and how do you do offshore? Do you anchor it to the floor with chains?
Yes. Well,
and then floaters, right?
Yeah. So the structure is a floater.
Right.
It's a hole. You can think of it as, so in our case, is small columns kind of far away. We kind of like a catamaran type of thing.
Right.
But you have different things. The turbine is on top. So your floater is the connection between the turbine and the seabed. And the floater has to ensure that your turbine works. So whatever limits you have on the turbine instead of motion, that floater has to make sure that those motions, there's no really motions, acceleration, so the second derivative, are acceptable. So you can make electricity. And then after that, you connect a cable, the electrical cable, from the platform, or that goes to the seabed and then back on. So that's how your electricity goes. Now, when you have this cable, we can only go so far within the watch circle, because otherwise you'll stretch it. So you calculate what is my overall limit. And then you design a mooring system that will hold those limits in all conditions. Your 50-year storm, your 100-year storm, and depending on, whether so you look at, for a site, where's the wind coming from? Where's the waves coming from? Where's the current coming from? And you set up an entire matrix of those conditions, and you run every single cases. And then you look at probability of those cases happening, and then you assign those probabilities as weight factors to your design, and that's how you do the design of your structure and of the mooring system. So lots of computation. I know you're a software engineer.
Yes. I love the computational challenge of that. Yeah.
So we gave a lot of money to Amazon the first few years. By the time we were giving more money than servers, we started going to data centers. But we have, we have two data. We rent space in 2 data centers, one in Europe, one here.
And just to run the calculations.
Oh yeah, and every year my IT team is asking for money for more servers and more space and things. So it's a big, offshore wind is very, very big in computations.
Right.
So, but again, you think that, but when you look at the cost of engineering versus the cost of the project, and extra, doing a little bit more engineering to reduce the cost is it's money very well spent.
Yes, because everything else is so expensive. The logistics, the transport, the building, and we're talking about big, heavy objects.
Yeah.
So
some of the vessels that we use in the wind industry, it's a range, but it's between, the small ones, between $50,000, $60,000 per day to $200,000, $300,000, $400,000 per day for the big ones with trains and all that.
Right.
That's a lot of money.
And you mentioned something that one of the forces that affects the most is, I understood it's the angular moment, right?
Yes.
Yeah. It's the one that, you collect more energy on that than anything else.
Yeah. So for us, so it's a very big, so a turbine, roughly, the tower is 100 meters up in the air, and you have a rotor diameter of around 200 meters. And so the tower is bigger. It creates tremendous overturning moment. And the bottom of the tower is connected to the structure. That's a transition piece. And that's what drives the entire design, the loads or the moment, the overturning moment at that piece. So everyone has to worry about that. And what's interesting is for the developers, you have a turbine contract and then you have a whole contract. And the responsibility for the loads is it's not very clear on who's going to take the overall responsibility of the design of that piece. So, we're figuring out, obviously, because we've done projects, but that's always very good discussions.
Right. So it's both a technical critical piece, but also, contractual legal, critical piece, because, defining those responsibilities becomes very critical. Yeah.
So we have a lot of this.
Right. Yeah. And I think that's the beauty and the challenge or complexity of engineering, right? That you're always having to balance between trade-offs. There's no single answer fits all, right?
That's right.
Yeah. And being able to achieve that level of modularity, that's a great achievement, because then you were able to, simplify that a lot.
Put it together and try to do a lot of them.
Right.
And the other problem is if you have one error and that error propagates, you might have yourself with a very, very big problem if you have to take all of your units back to shore to fix something.
Right.
So reliability is very important. So to do those large projects that we're talking about, you have to start by doing pilots. And then you have to do, smaller pre-commercial projects. And then after that, you have to do those commercial projects, but you have to do those pre-commercial projects with the same systems that are going to be commercial. One of the things that we've noticed over the last few years is the turbines have grown very, very big, from 10 to 20 megawatts, because the economics are better. But then we had the big break from the turbine manufacturers saying, you're asking us to put warranties on a turbine, but we just don't have enough experience. So we're not going to sell you those turbines because you're asking for warranties and we might jeopardize our company. So we're going to stick to the ones that we know. And so the developers are yeah, but those are too expensive and they don't really work. And the turbine suppliers are saying, well,
Right.
too bad, so sad.
Because they see the numbers of the big ones and they say, well, I want that one.
Well, no, but but then they also want, so the developers also want, okay, so those are this, but if there's a problem, it's on you. And so we need to have pilots and pre-commercial projects with the bigger ones to reduce the risk so that we can go to the bigger projects. So it's not because we've done, for our industry, we've done almost 300 megawatt of floating wind projects. The biggest turbine is a 10 megawatt. The design of a 10 megawatt and the design of a 20 megawatt is very, very different. Just the natural frequency of the tower is, in one case, in between the blade, one blade rotation and three blade rotation. It's called a soft stiff. And the other case is past the rotation of the 1P and 3P. So that changes the entire fatigue calculations and everything. So we can't not retest and redo through the cycle, which makes the entire industry kind of slow down. So every time, the developers are like, oh, we need this and that. And they're slowing down the industry by not wanting to do smaller projects that are more safe. But they can't because they have to meet the numbers. So this is kind of why floating wind is taking some time to get there. We'll get there for sure.
Right.
And there's actually now free commercial projects that are going to be sanctioned and start in France, in the UK, in Norway, in Japan, in Korea. Korea is already a bit bigger, but the 100 megawatt, 200 megawatt type scale project, by doing those successfully, then you'll be able to do the 500 or 1 gigawatt project in post 2030.
Right. Interesting. So you're still developing the technology, and that becomes critical to be able to implement larger scale project.
So we're kind of lucky because we've been developing the technology since the first one, 2007, 2008. By circumstances, we ended up starting a new company in 2019, Ossurgy, just before COVID. And
great moment to launch a new company.
Oh, it was amazing because no one,
really?
And we're a very small industry, so everyone's worried about their own thing. No one's wondering what is Alessia and Christian and Dominique doing and things like that. And we come up in 2021 with a new concept, new investors, new name, new everything. And a pretty cool concept that really addresses those points of industrialization with the lightest floater, with all that. And we went kind of from being can we make it? Can we be like the last technology that makes it? And there was projects in Korea where, they start with an RFQ with 32 projects and they put us in. And then then they pre-select or they cut half and with the last one to be selected. And then they go from like 16 to 8 and then they pay a little bit of money. Then they go to 4 and we're the last one in. Every time we're like trying to get in. So that was fun. But we went from that to, kind of being a reference. When people talk about offshore wind, they're like, oh, so now it's like, oh, Ossurgy is that solution. They're still new. They don't have a pilot. So obviously everybody else says they don't have a pilot. But they don't have a pilot at the 18 megawatt scale anyway either. So we kind of caught up and kind of now we're kind of catching up. And because we did not have a floater that we tried to industrialize, but we designed a floater for industrialization. And this is where I said that we were lucky because we came at that time where we knew what was needed and we could start with a clean slate. That kind of was good. And then we were lucky we have great investors, Chevron, Total Energy, Octopus, High-Tech Vision, very, very big name. In the end, High-Tech Vision created a company that then was sold to Offshore. So Offshore Wind is our partner there actually right now. We work together, but they have the lead contract on our pilot. It's a 3 megawatt and it will be installed in the spring in the middle of the North Sea. So we're catching up. So we have a lot of support behind us.
Right.
So,
That's amazing. I mean,
it's cool.
You're changing the industry and you're building these huge machines.
Yeah.
that has to be cool too, because when I build software, you can see it on the phone, right? But when you build something, you can see it in real life, right?
Yeah.
And
So I was going to take my board to the site in Verdulen. Well, the thing is, we're going to do it a little bit later. We'll do it in March. So the days are a little bit longer, so they can see it. But just 18 people that have invested in you, but that are not really part of this, seeing those structures and how big they are and how everything. I mean, that you can look online and, there's some pictures and like the column is this big and the person doesn't even make it to the bottom. That's, it's 20 meters tall structure and, 60 meters in diameter, in radius. Yeah. Is, more, it's about 70 meters in diameter. This one, they're big. They're big. So
that's huge.
yeah.
Yes. And you mentioned that you're planning to then industrialize the process, right? What are your plans to do that? Are you planning to build a factory in Europe?
No. So the plan for industrialization, and a lot of people, I'm happy you asked that question, because a lot of people say, okay, we're going to build those factories. We're going to build, a concrete factory, and the government is going to give us that much money to build that so we can do those projects. But are we going to make those stays, 400 or 500 square meters and spend a lot of money on that? For me, that's not industrialization. For me, industrialization is looking at the supply chain that you have. What are the case? What are the limitations? What are the yards? What can they do? What can you roll? So in terms of steel, you can roll a 10-meter column that's about 15 centimeters thick. So we're talking about, big steel. Pretty much everywhere in offshore yards. And monopiles right now, so when the monopile is when the bottom fits, when the seabed goes into the bottom, you start finding yourself rolling 14, 15 meter towers, circular sections, cylindricals, at about 20 centimeters, something like that, more. So more than the capacity of those rollers. So now you have to, in your cost, include the fabrication of the machine. And someone has to pay for that machine, and it's your project, and there's not that many machines in the world, so the price goes up. So be able to stick to what you have and improve it a little bit. So I'm not saying don't spend any money, but I'm saying improve to what you can do without jeopardizing the cost of the project. So make your stay stronger, because we have to put a big crane. So put a mat, redistribute the load. Your channel is 9 meters. Okay, dig it to 11, 12 meters. Most yards, most ships offshore, the water depth of commercial harbors is 12 meters. That's an LNG tanker. And there's very few that are 16, 17 meters. There's quite, Port of Rotterdam, for example, for very large tankers. And there was this whole thing that's happened, in the late 90s, is we start building very, very large, they're called very, very large tankers,
right.
VLCs.
Those are the ones that cannot go through the Panama Canal.
Right, and they don't really go into the harbors except a few. So you offload the oil and gas offshore. So you do offshore offloading.
Right.
So you go to a smaller one that then comes in. Great concept in terms of, okay, you're transporting all those things, but economically, it's very difficult to, go into other harbor and do those things. So so there's not that many yachts that gets there. So if for floating wind, we have to use those yachts because our draft is at 15, 17 meters, we just cut us off of all Japan, because there's no harbors in Japan that have those water depth. Most of, except a few in Europe and in Korea, that's about it. So we have to stick to what we have with, obviously upgrades, buy new rollers, buy automated machines for welding and things like that. So you're not manually welding thousands of kilometers of welds. And then your welds are better, they're more precise, so your structure is better. So there is improvement and money that needs to be spent. But don't go crazy, because then the projects will not happen.
Right. So if you reuse the tools that are available, you can lower the cost significantly.
Yeah. And then going back to your Toyota production system, is now you start managing your suppliers. So you always have a little bit more suppliers than you need. So if one drops, you go back to the other one and the next one. So you always keep them busy and you shift around and you look at your loads so that everyone's busy, but you always have capacity. Because if you lose a yard and that's the only yard that can do something, and then you have to go sign a contract with someone else, you just lost 4 months on your project.
Right.
And that's expensive. So you have to build that redundancy in your supply chain.
Yeah.
And so to build that redundancy in your supply chain means that you have to have a very big supply chain, means that you have to know what's out there and be able to work with everyone. So, for us, so we can build, of course, the structure, we can build them in Korea, we can build them in China, it's probably cheaper. But we have yards, there's yards in Turkey, there's yards in Greece, there's yards in Italy, there's yards in Spain. We work with all of them. And so we build the Ossurgy data, we build it in Vodosplit, in Split in Croatia. And the Ossurgy wind was built in Dimitros in Greece. But then we also have Fincantieri in Italy, we have Charles in Spain, and so on. So, and Spain has built a lot of others. Navantia has built a lot of other things for the North Sea. So we're working with everyone. And we have to keep everyone busy, and everyone has to know what we do so we can always go back to them. That's for me, that's a very big part of industrialization.
Yeah, and also logistics, right? Because if you have to, ship it from the other side of the world, it's going to be much more expensive. If you can do it locally, even if it's a little more expensive, you're still saving money, right?
And so that's also, so if you look at what people do now is they build the entire structure and then, how big they are. So you can put one per boat. And so those are the big boats that transport or platform. Right. So it's a flat deck and the boat kind of lowers itself underwater, keep your stability.
Yeah.
You put the platform on, you raise back up, and then off you go. We're different because I told you we were bolting the structure. So we're kind of the IKEA of offshore wind. You get a big box, you get the bolts, you get the frame, and you get all of your things. And so now instead of taking one unit and transporting a lot of empty void, and it's not that heavy, we just pack the columns, we pack the trusses, we pack everything on the back of the vessel. So it's the same vessel, but it's completely packed. So now instead of transporting one or maybe two structures, but if the storm megawatts is probably one, we can take 5, 6, or 7 on one boat.
Oh.
So, or we take 2 boats and one does columns, the other one does trusses. And then if we do that, then we don't even have to go to the same yard to fabricate the column and the trusses. So all of a sudden now you start looking at what yards can specialize and do 2 columns, center columns, outside columns, and trusses in the middle. And some of it might be actually done locally. So now you're actually using local content. But you have to understand what can you do? So if it's in the UK, it's very different than, if you're in France or if you're in Italy, but you can always do something. In France, you're not going to be fabricating cutting steel. We just don't have that type of capacity. But we can use the harbors to do the assembly. And so if you look at, the Celtic Sea, for example, so you're around and you don't really have that much facilities, but you can still fabricate some things in the UK. And then you can turn around and bring them out and things like that. So there's a lot of trying to, as you said, local content, if you do it right, is cheaper because you're not cheaper and faster because you're not spending time transporting. But you can't remove transport altogether. You just have to do it efficiently.
Yeah, but it's different if you can, just do a shorter transport than a longer transport.
That's
right. Because every mile, every knot.
And you're burning fuel.
Yeah. So. Plus these are heavy machines, these are heavy objects that are going to take a lot of resources, right? To transport. Yeah. So we were talking about CO2 and climate change. How is this floating devices are going to reduce or going to impact on climate change?
Yeah. So when you look at generation of electricity for the next 25 years, you compare a wind turbine to a gas plant. And I'm going to talk in very, very broad terms, but it's a turbine. So it's something that spins, there's magnets around, as you spin, a magnet will call you trade electricity, and then offloads the electricity. It doesn't really matter if your turbine is $1 billion, or if like 20 to 50 turbines is like $2 or $3 billion, because what happens then is what makes it spin. And in one case, is 20 or 25 years of gas that you're burning. And you trade your explosion, and that turns, and off you go. And in the other case, it's free wind. And when you look at the economics of a 25-year project, your capex is a big part for your financial, but your money is coming from the 20 years and your revenues are coming from that. But your carbon footprint, yes, okay. So you have to look at what is the carbon footprint of your device, but you also have to look at the carbon footprint of the operation of the device over those things. And then sometimes after 25 years, you say, great, can we increase it to 30 years or 35 years? And usually,
Right.
So there's a whole discipline called life extension. There's a name for it. And a lot of people, do not want to decommission because that's expensive. You look at the platforms here in California or even in the UK, the oil and gas platform, everyone's trying to find something so you don't have to remove them. And there was a lot of talks about putting wind turbines on the Santa Barbara platforms. So that's the main thing. We're not going to be burning gas for 25 years. And then obviously you have to worry about the LCA of your steel. Where is it coming from? Steel is completely recyclable. So you can take your unit, you can make new steel out of it. So then you have to look at, okay, so what is the LCA of the fabrication? And that goes back to what I was saying with, if you don't have to fabricate new tools, but use the tool that you have.
Right.
That's very important. With Christian, my partner, we always have those discussions. So a few years ago, a long time ago, when the Toyota Prius came in, he bought one. And I was driving, I was driving a 4Runner. Big, kind of like big black, truck. But I said, I'm more green than you because you have a brand new car that has 2 engines and a battery. And my car's 10 years old. I'm going to drive it until it's cost me more to fix it than to recycle it.
Right.
And I drove it for 15, 16 years. So, it's you have to look at the entire thing.
Right.
So he drives a Tesla now and I have a sailboat.
Right. Right.
So we're very conscious of burning gas and so on. So
yeah, and when the first time you were talking about the floating devices, I was thinking that you were building it with cement, like this World War II floating things they did. I don't know why I thought that, but in my mind,
there's quite a few people in the industry that believe that concrete is the solution. I disagree for a few reasons. One, if you look at the economics of the device itself, okay, fine. Right. But you never include the factory in your calculations. If you include the factory, we're a lot cheaper. But it's also not just that. When you're talking about 5-10 units and you can do them in 1 year, it's fine. But now you have, a floater in concrete is like 5 to 10 times the weight. So you have, if you're doing a gigawatt, just a simple question, where is the sand going to come from? You're not talking about tons. You're talking about thousands of tons of sand that you need to bring in. So, the entire thing kind of breaks down. And how long does it take? Because there's a project, there's 3 projects in France, in the Mediterranean, that were assigned that were granted by the government in 2016. And the first project was an EDF project that was put in the water 2 years ago. Then the second project I used to work on that was put in the water this year. And then the third project is the heaviest. So it used to be concrete, then it becomes steel and things like that. But it's just very, very challenging and very big. So your mooring is more expensive, everything is more expensive. And people say, okay, concrete is recyclable. but not really. You don't turn concrete back in concrete.
No, because it goes through a chemical process, so it's not easy to turn it back.
Yeah.
Yeah.
So
and the manufacturing process creates a lot of byproducts that are
so. And then you're talking about efficiency and so on. It goes back. Can you put 10 units on or 5 to 10 units on the boat, or is it just one?
Right.
And your footprint. And so then the time it takes is just much longer. You cannot. We have a hard time with a 3,000 or 4,000 ton structure to do, one a week. And now you want to do one a week on the 15 to 20,000 ton structure. It's just not gonna happen.
Right. So, right.
But
that's interesting. Yeah, that's interesting. I mean, I didn't realize that there was such a close competition between cement and concrete.
I don't think it's that close. I think that there's some very, very tenacious people that want to see concrete, and everyone else is trying to tell them, yes, but it's not. It's not gonna work.
Right.
So,
right.
But
I thought that with concrete, the issue that you have is that they get flooded, so you have to keep pouring out water out, and then with steel, what I would be concerned is oxidation and things like that, right?
Yeah. So no, concrete works offshore. I mean, there's a lot of oil, not a lot, but there are some oil and gas platforms that were built. But so there's two things. Is one, if it's a fixed structure, then it's much easier. Right. If it's a floating structure, then you have oscillating loads. And concrete works straight in compression, not really in tension. It would just straight on. But when you have, a ship, you have just this mode, so hogging and siding, because your ship does that all the time in waves, just it flexes back and forth. So you cannot do that in concrete. So what you end up doing is you have a steel frame in it, this rebar, and then so preform, and you pull on them. And by pulling on them, so you extend them. Steel is not like a rubber band, but it will move. And then you pour your concrete, and then you put it back together. So now it's not like having so you've pre-stressed it basically. Yeah. So what happened is it's not like a rubber band that you've extended. Now your rubber band will go back and forth, not enough to break, and not enough that it goes slack. And so you have to work within that range. So it's not cheap to build this, Right. So there's not too many vessels. There are some. I had a friend that built he had a 50-foot sailboat, and he made it himself in concrete.
Oh, wow.
Yeah. So it works technically, but it's not simple.
Right. Yeah, I understand that, if you pre-tension, then you can create a stronger structure, right? Yeah. But now you still have the issue of oxidation, right? If you don't cover the steel, right?
Yeah. But steel structure, we have 3 different ways of working with corrosion protection. Painting is the first one, and painting schemes are getting better and better.
Right.
They're expensive. They're not very clean. So what we try to do is use anodes. So it's just like the same as your motor, your harbor, your sailboat or your motorboat has a little piece of an anode at the base. So the anode will corrode.
It's a sacrificial.
Exactly. So we corrode first, and then you change them. And then the last part is compressed current. And in France, for example, your anodes have a little chemical that goes in the water, so it's not really. It's difficult to build big structures, but you put compressed current, so now you change the polarity of your structure, right? So it just doesn't corrode. So there's lots of different ways.
Yes. Which is something that we should also check on our water heaters. There's also an anode there that we need to change.
There you go.
That nobody does. Yeah. I haven't done until I tried. It broke the whole thing. I had to replace the whole heater. Yeah.
That's true. Yeah, no, I changed my anodes. It's cheaper than changing the popular.
Yeah. But it got stuck in a way that we couldn't get it out. So anyway, every time I know people talking about that, I remember. Yes. Yeah. Awesome. So we've been talking for a while.
I thought you would go fast.
So before we wrap it up, I wanted to ask you about, like, what if you have a young engineer, naval architect that is listening, right?
Yeah.
What recommendation would you give them, and what could they do to contribute to fight against global warming?
Yeah. So we were talking at lunch about this new generation that is so much more connected through Instagram and TikTok and this than us. We used to be, we didn't have that, and now we barely know how to use it sometimes. But this is the amazing, this tool that you guys have, because you can start playing with video games and world blocks and all those things, but you can also mobilize ourselves, and it's your planet. The thing, there's no plan B, or there's no planet B. It's yours to save. Our generation, can I speak French? We fucked it up for you. And some of us are trying to make it better. But we're not being very successful. And, we have politicians that don't care, that just want to make more money for themselves. And somehow I wonder whether those people have kids, and whether they care. Maybe they have kids and they just have enough money for their kids. But in what planet do they want their kids to grow up? So we made it. We showed you that we have a problem, but we can't fix it for you. So I'm sorry. But you have to do it yourself. Wow.
Yeah,
I didn't think that was going to happen.
It's hard, like when we see our kids growing up, and they're going to grow, in a different world, different opportunities, different situations that we did.
Yeah.
Yes.
Sure.
Yes. So Dominique, thank you very much for joining us today. Yes.
Yeah.
We learned a lot, and I appreciate it. Yes.
Thank you. It was fun. It was really good talking about all this. And we had the perfect weather. So
yes, it's a beautiful marina, and thank you for choosing this place, because I know it's special for you. So thank you.
Yeah. All right. Thank you.